Hello, my name is Rachael Abbott and I'm currently a PhD student at Queen's University Belfast and sponsored by Tallies UK. Today I will be presenting my paper titled Unsupervised Object Detection via Long-Wave IR RGB Translation. I will now give an overview of the problem space. It is necessary to achieve 24-hour surveillance capabilities to reduce the cognitive burden on operators in a land vehicle scenario. There are many problems associated with current detection systems that include they are mainly trained using RGB imagery and require large datasets for training. In addition, there is a severe lack of IR datasets which are extremely expensive to collect. Synthetic imagery could provide a solution to this problem. However, there are many issues associated with current translation methods. For example, there is a lack of research using long-wave IR RGB modalities, non-corresponding datasets, and datasets taken in uncontrolled urban scenes. There is also a lack of detection in synthetic imagery. We address all these issues in the paper and present two approaches for detection in real long-wave IR and synthetic RGB imagery using unsupervised methods. Displayed is an overview of our first approach. We translate the long-wave IR to RGB. The synthetic RGB imagery is then passed to an RGB detection network. This removes the need for large labelled long-wave IR imagery for training. In addition to testing the synthetic RGB imagery, we combine the synthetic RGB with the original long-wave IR and test it. This is to maintain structural details and improve F1 scores. We enhance the quality of the synthetic imagery produced by enhancing the cycleGAN network with our novel object-specific adaptation. The right-hand side of the diagram on screen depicts the normal cycleGAN architecture. For our adaptation, we pass a long-wave IR image through an RGB trained detector adapted in an unsupervised way for IR imagery. We calculate the difference between the objects detected in the real and recovered images and add it to the normal cycleGAN loss when training. On screen are the results from our first approach. It is clear that our adapted object-specific cycleGAN produces the best quality synthetic RGB imagery across both the FLIR and Tallies datasets. The Tallies datasets produce the best quality synthetic RGB imagery. This is because this dataset has a constant background and a maximum of 6 objects per frame, which therefore helps to produce better quality imagery. The FLIR dataset has many more objects, clutter, occlusions, and constantly changing background. Fusing both the synthetic RGB and real long-wave IR images together for detection improve the overall F1 scores. We'll now discuss our approach 2. Real RGB imagery is translated to synthetic long-wave IR. These synthetic long-wave IR images are used for fine-tuning an RGB trained detection algorithm, and we test the real long-wave IR on this network. When testing the Tallies and FLIR real long-wave IR imagery, we achieve F1 scores of 85.6% and 45.6% respectively. These results are comparable to the F1 scores produced when fine-tuning with real long-wave IR imagery, but with the crucial advantage of not requiring extra annotation. This method produces higher F1 scores than those in approach 1 and shows how accurately we can detect in long-wave IR imagery using no real long-wave IR images or labels for training. To conclude, we propose an unsupervised adaptation to the cycleGAN network. We show long-wave IR to RGB translation is possible between non-corresponding datasets containing cluttered urban scenes. The synthetic RGB images can be used for detection in RGB trained algorithms with F1 scores of up to 67%. Moreover, this paper is the first to fuse RGB and real long-wave IR, further improving F1 scores up to 73%. We create synthetic IR imagery and show for the first time that this imagery can be used for effective training of deep learning detectors for improved detection in real long-wave IR data with F1 scores of up to 85%. Thank you.